This question is about isomers. Give a reagent and observations for a test tube reaction to distinguish between 2-methyl-butan-1-ol and 2-methyl-butan-2-ol. So we've got a primary versus a tertiary alcohol. So what we're looking at here is that tertiary alcohols cannot be oxidised, but primary can. So we want to use acidified, so H2SO4 potassium dichromate, K2Cr2O7. You could write that in words if you're not sure of the formulas. Acidified potassium dichromate. With the primary alcohol, we'll see the orange solution turns green, because it can be oxidised, therefore reducing the dichromate to chromium 3. And with 2-methyl-butan-2-ol, the tertiary alcohol, the orange solution remains. No change in colour because we can't oxidise a tertiary alcohol. So you could write no observable or no visible change. Compound A and B both have a molecular formula C4H8Br2. So if we're looking at that, this looks like it's saturated because it's got 2N+2 substituents. A has a singlet, a triplet and a quartet. Now a triplet and a quartet often tells us that we've got a CH3CH2. And then we've got another singlet, so there's sort of like a break between that and where the remaining protons are. So there's 8 protons altogether, and we know that we've probably got an ethyl group. So that means that we've probably got CH3CH2, and then a C, and then another CH3 singlet, and there are no hydrogens on this C, so we're going to put both Brs on this C. B only has 2 singlets, so all 8 hydrogens are split into like 2 sets of equivalent ones. So it could be that there's 4 of one and 4 of another, or it might be that there's 6 of one type and 2 of another type. These are the sort of probabilities. 4 of one type and 4 of another type would be quite difficult with only 4 carbons. So it's more likely to be the other 2 singlets, it's proton and MR. So you kind of have to play around a bit. So we've got 4 Cs. If they were in a line, or a straight line, and we tried to put our Brs on, we wouldn't end up with, because you would end up with like 3 H's. If you put your Brs on the end, you would end up with splitting, not singlets, so we can't have that because we can't have adjacent. So let's try and see, if we put 2 methyl groups, that would be 6 identical, so there would be, and if we put a Br here, that would be a singlet because there's no hydrogens on this central carbon, which leaves us, that's 3 of the carbons, which leaves us 1 more carbon. It leaves us with 2 H's and a Br, and if we just put the H's on there, because there are no hydrogens on the next door neighbour, then this is our structure. So let's just put that in the actual space. You can draw that skeletally or displayed, or this sort of structural way that I'm doing it. C6H3Br3. So this is kind of having the formula CnH2n. So cyclic, perhaps. Sorry, not even H2n, HN. It's got an equal number of substituents to carbons. So that actually means it's probably benzene, because benzene would be C6H6. But we've got 3 Brs on. And we want to put those 3 Brs on so that this one only has 2 types of carbon and this one has 4 types of carbon. So let's draw our benzene ring. Let's not forget the pi bond, otherwise it's just cyclohexane. If we only want to have 2 types of carbon, we need the type that has Br and the type that doesn't, and so we're going fully symmetrical on that, and then there would only be 2 types of carbon. If we want to have 4 types of carbon, then we need less symmetry, and there's possibly more than one right answer, but let's just try. So if we put a Br here, and then a Br here, and a Br here, we can just play around with it. This would have carbon type number 1. These two would be identical. These two would be identical, and this would be different. So that works out. E, F and G are isomers. Figure 1 shows the infrared spectra, but not necessarily in the same order. We just have to line them up. So remember, we're going to highlight the fingerprint region and get rid of it, because we're not interested in that. So we'll just get rid of the fingerprint region. Now we need to look at other peaks we've got. So this is at around about 1750, so this is probably a C double bond O. This is also a C double bond O, as is this. So we've got C double bond O in each compound. If we look up, we can see that's true. In this compound here, we've got no OHs at all. We've just got CHs. Here we've got an OH, and this is an OH in an alcohol. So, and then the CH is next to it. And then here, this one that looks like an upside down mountain, this is an OH in a carboxylic acid. So let's go back up. Which one doesn't have an OH? And that would be F. So we'll put F in this box. Which one has an OH but not a carboxylic acid? That would be G. And then last but not least, the one that's a carboxylic acid, that would be E.